Hi, here we are in Highlights Part 2, where we're going to be talking about 4 important properties of the gradient vector. Now, in the last video, we defined the directional derivative of a function at a point in the direction of a unit vector u as the dot product of the gradient of that function at the point a, b with the unit vector. You may remember something about dot products, another way to compute them, and that would be the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. So let's do it that way. Wait a minute, is something missing here? I said the magnitude of the first times the magnitude of the second, but I don't see the magnitude of u. Why not? Oh, right, it's a unit vector. I don't need to write a 1 here. Okay, well, one thing we want to know is when would this derivative, this directional derivative, equal 0? And there are 2 ways it could happen. One way is if the gradient vector is actually the 0 vector, so it has a magnitude of 0. So if the gradient vector is the 0 vector, then all directional derivatives of the function at that point will be 0 because, of course, this term would be 0. Of course, another way that the directional derivative could be 0 is if this dot product is 0, meaning these 2 vectors are orthogonal. So part 2 of that, and this is maybe a little more significant, the directional derivative will be 0 in any direction the unit vector u is orthogonal to the gradient vector. Okay? So important point number 1, let's put a star next to that and move on to part 2. Now, once again, looking at the directional derivative as the magnitude of the gradient times the cosine of the angle, well, we know that something about the cosine function. The greatest it can be is 1. And so the greatest rate of change, assuming that, of course, that the gradient is not the 0 vector, the greatest rate of change of the function at a point occurs when the cosine is equal to 1. So the cosine is the cosine of theta. Theta is the angle between the gradient and the unit vector. When would that angle have a cosine of 1? It would have to be an angle of 0 degrees or 0 radians. So that means that the greatest rate of change would be in the same direction as the gradient vector. And of course, the value of that greatest rate of change would be the magnitude of the gradient, because we're saying that cosine theta would equal 1 there. So we sometimes call the gradient vector then the direction of steepest ascent. The quickest rise of the function would be going in the direction of the gradient at that point. The flip side of that one is what's the least the cosine theta could be? Well, that would be -1. And so, if we're dealing with a non-zero gradient vector, then the least rate of change would occur when the cosine theta is -1. That would mean the most negative slope or the most negative rate of change. And of course, when these 2 vectors have an angle between them with a cosine of -1, that angle would have to be pi, or 180 degrees. That would mean they're in opposite directions. So we say that the least rate of change, the most negative rate of change of the function, is in the direction that is opposite the gradient, and the value of it would be the negative magnitude of the gradient vector, because again, this cosine theta would be -1. So in this case, we say the opposite of the gradient vector gives the direction of steepest descent. Okay, so we had, when we get a directional derivative of 0 in a direction that's orthogonal to the gradient vector, we have direction of steepest ascent, and now steepest descent. And now just one more property I want to tell you about gradients, and that is their relation to level curves of the function. So remember, here's a level curve. This is where we set the function equal to a constant. Here that level curve has been just projected down to the xy plane. Now, this red vector here is a tangent vector to the level curve. And we did prove in class, if you had class, that the gradient is orthogonal to the level curve. That means it's actually orthogonal to the tangent line. So here I've got a red tangent line and a blue gradient vector, and hopefully you see there's kind of a right angle there. This was a pretty easy thing to prove. Now, since the gradient is orthogonal to the level curve or orthogonal to a tangent to that curve, we can actually use that fact to write an equation of a tangent line at a point in a very cute way. Now, we're talking about a tangent line on a two-dimensional curve. Okay, so this blue gradient vector is orthogonal to this red tangent vector. So I'm doing the dot product of the gradient at that point with, now x minus a, y minus b represents, if I let x and y be the coordinates of some point on this red vector, well, you see x minus a would be one component, and the first component, y minus b, would be the second component. So because the blue and red vectors are orthogonal, this dot product would be 0, and that would actually give us an equation of the tangent line. Very different from y equals mx plus b, but can be rewritten in that form. Okay, well, you'll see some examples of this in a later video, but I'm going to stop right here because this is the end of our highlights. Thanks for watching.